Now that we hopefully have a conceptual understanding of what a surface integral like this could represent, I want to think about how we can actually construct a unit vector, a unit normal vector at any point on the surface. And to do that, I will assume that our surface can be parameterized by the position vector function r, and r is a function of two parameters. It's a function of u, and it is a function of v. You give me a u and a v, and that will essentially specify a point on this two-dimensional surface right over here. It could be bent, so it kind of exists in three-dimensional space, but a u and a v will specify a given point on this surface. Now, let's think about what the directions of r, the partial of r with respect to u looks like, and what the direction of the partial of r with respect to v looks like. So let's say that we're at some point uv. So for some uv, if you find the position vector, it takes us to that point on the surface right over there. Now let's say that we increment u just a little bit. And as we increment u just a little bit, we're going to get to another point on our surface. And let's say that other point on the surface is right over there. So what would this r sub u vector look like? Well, its magnitude is essentially going to be dependent on how fast it's happening, how fast we're moving towards that point. But its direction is going to be in that direction. It's going to be towards that point. It's going to be along the surface. We're going from one point of the surface to another. It's essentially going to be tangent to the surface at that point. And I could draw it a little bit bigger. It would look something like that. R sub u. So I've just zoomed in right over here. Now let's go back to this point. And now let's make v a little bit bigger. And let's say if we make v a little bit bigger, we go to this point right over here. So then our position vector r would point to this point. And so what would r sub v look like? Well, its magnitude, once again, would be dependent on how fast we're going there. But the direction is what's interesting. The direction would also be tangential to the surface. We're going from one point on the surface to another as we change v. So r sub v might look something like that. R sub v. And they're not necessarily, these two aren't necessarily perpendicular to each other. In fact, the way I drew them, they're not perpendicular. So r sub v's look like this, but they're both tangential to the plane. They're both essentially telling us right at that point what is the tangent, what is the slope in the u direction or in the v direction. Now, this is when you have two vectors that are tangential to the plane and they're not the same vector. These are actually already specifying, these are already kind of determining a plane. And so you can imagine a plane that looks something like this. If you took linear combinations of these two things, you would get a plane that both of these would lie on. Now, we've done this before, but I'll revisit it. What happens when I take the cross product of r sub u and r sub v? What happens when I take the cross product? Well, first, this is going to give us another vector. It's going to give us a vector that is perpendicular to both, to r sub u and r sub v. Or another way to think about it is this plane that when you take the cross product, this plane is essentially a tangential plane to the surface. And if something's going to be perpendicular to both of these characters, it's going to have to be normal to them, or it's definitely going to be perpendicular to both of them, but it's going to be normal to this plane, which is essentially going to be perpendicular to the surface itself. So this right over here is going to be a normal vector. This is, I'll write it, well, let me just write it this way. This is a normal vector. I'm not saying the normal vector, because you could have different normal vectors of different magnitudes. This is a normal vector when you take the cross product. And we can even think about what direction it's pointing in. And so when you have something cross something else, the easiest way I remember how to do it is you point your you point your right thumb in the direction of the first vector. So in this case, r sub u. So let me see if I can draw this. I'm literally looking at my hand and trying to draw it. So you put your right thumb, so this is the right-hand rule essentially, in the direction of the first vector. And then you put your index finger in the direction of the second vector, right over here. So this is the second vector, so that's the direction of my index finger. So my index finger is going to look something like that. And then you bend your middle finger inward, and that'll tell you the direction of the cross product. So if I bend my middle finger inward, it will look something like this. And of course, my other two fingers are just going to be folded in like that, and they're not really relevant. But my other two fingers in my hand looks like that. And so that tells us the direction. The direction is going to be like that. It's going to be upward facing. That's important because you're two normal vectors. There's two directions of normalcy, I guess you could say. One is going out like that, outwards, or I guess in the upward direction. One would be going downwards, or going, I guess you could say, into the surface. But the way I've set it up right now, this would be going outwards. It would be a normal vector to the surface. Now, in order to go from a normal vector to the unit normal vector, we just have to normalize this. We just have to divide this by its magnitude. So now we have our drum roll, the unit vector, and it's going to essentially be, a function of u. It's going to be a function of u and v. You give me a u or a v, and I'll give you that unit normal vector. It is going to be equal to the partial of r with respect to u crossed with the partial of r with respect to v. That gives us a normal vector, but it hasn't been normalized. So we want to divide by the magnitude. We want to divide by the magnitude of the exact same thing. R sub u crossed with r sub v. Crossed with r sub v. And we're done. We have constructed a unit normal vector. And in future videos, we'll actually do this with concrete examples.